All right. Okay, so welcome back, everyone. I hope you had a good night's sleep and digested everything from yesterday. So today should be a shorter day and a bit more relaxed. I only have stuff for like 1.5 hours, and then we can talk a bit or just do a longer break before the talks. Just as a short disclaimer, so I'll be talking about reinforcement learning in other fields, but I'm not an expert in any of these topics that I'll talk about today. But I thought it would be really interesting to mention them because it just shows how reinforcement learning isn't just there to solve optimal control problems and to play games really well, but that you can use reinforcement learning actually to try and understand animal behavior, learning, and also like psychological conditions in humans, for example. So I think it's a super interesting outlook, and some of the stuff that really made me also excited about reinforcement learning, to actually use it to understand how certain processes work in the brain. And yeah, the topics today are heavily influenced by 2 chapters from the Sutton and Bartu textbook. So if you want to read up more on it, just check out the free PDF online. There are 2 chapters on this that are very good, have also nice references to other sources if you're interested in this stuff. Okay, so let's dive right in. So first I'll talk about reinforcement learning in psychology, and then later reinforcement learning in neuroscience. All right. So the first time something that sounds kind of like reinforcement learning was mentioned was by Edward Thorndike in 1911. He's an American behavioral psychologist trying to study animal behavior. And he basically said, of several responses made to the same situation, those which are accompanied or closely followed by satisfaction to the animal will, other things being equal, be more firmly connected with the situation, so that when it reoccurs, they will be more likely to recur. Those which are accompanied or closely followed by discomfort to the animal will, other things being equal, have their connections with the situation weakened, so that when it recurs, they'll be less likely to occur. Okay, so overall, the greater the satisfaction or discomfort, the greater the strengthening or weakening of the bond. Okay, sounds a bit like reinforcement learning, right? And actually, we can draw some parallels from classical and operant conditioning to policy evaluation, policy improvement, what we talked about yesterday. So classical conditioning is the idea that animals predict future states or stimuli, so they can predict expected reward or punishment, for example, after some learning. And that can kind of be compared to policy evaluation, so predicting future values of states. And then there's operant conditioning, which compared to classical conditioning, there is, so the reward is now conditioned on the animal's behavior. So the animal learns to adapt the behavior to receive more reward. And this is a little bit inspired by the law of effect. So in operant conditioning, the stimulus is actually contingent on the behavior. And there's some overlap between those two, but those rough parallels can be drawn. So policy improvement, adapting the policy such that more reward can be obtained overall. And I'll be talking about both a little bit and how they compare to reinforcement learning and also some experimental evidence. Okay, so first of all, classical conditioning. So the magnitude and timing of the conditioned response changes as a result of the contingency between the conditioned stimulus, conditioned stimulus and the unconditioned stimulus. And that was proposed by Pavlov in 1927. But what does it mean? So let's just explain it on this a classical example of Pavlov's dog. So there is an unconditioned stimulus, which in this case is food, which elicits an unconditioned response. So the dog produces saliva, which makes sense evolutionary, so it can start eating the food and digest it better. And then we have a neutral stimulus, which is a bell. I think in the original experiment it's a metronome, but I can draw a bell better, and it's easier to say, so let's say it's a bell. And the bell is neutral because it doesn't elicit any response without training. Okay, so we have this unconditioned stimulus, the food, and the neutral stimulus, the bell. And then we do some learning. And in learning, we ring the bell, then we present the food, and because of the food, the dog begins to produce saliva, the unconditioned response. And we repeat this multiple times until after learning, okay, the food still produces the unconditioned response like before, but now the bell became a conditioned stimulus and now produces a conditioned response. So the dog learned to associate the bell with the food, and now only the ringing of the bell without presenting the food elicits this conditioned response, so producing saliva. So the neutral stimulus became a conditioned stimulus. And the food is the thing that led to change in behavior and is therefore called a reinforcer. Is that clear so far? I guess most of you are familiar with classical conditioning roughly, but if you have any questions, feel free to interrupt. Okay. So there are two types of conditioning. There's delay conditioning, where we have an interstimulus interval between the onset of the conditioned stimulus, so in this case the bell, and the unconditioned stimulus. So that would be ringing the bell, and then after some time you put the food inside of the dog. You keep ringing the bell. And then we have trace conditioning, where we have a trace interval, which is this. Oops, hello. Can I draw here? I don't know. I guess I can't draw on top of it. This is the trace interval. So basically, we ring the bell, then there's a short break, and then we present the food. Okay. So that's basic classical conditioning. And then we have certain phenomena which we can observe in behavioral experiments. So one phenomenon is blocking, which means that when a conditioned stimulus and conditioned response combination is learned, so after the bell and the salivation combination is learned, then an additional neutral stimulus is added. This new neutral stimulus is not associated with the conditioned response. So let's say the bell has been learned, like shown before, and now additionally to ringing the bell, we turn on the light bulb. And we train this multiple times, and then we test if turning on just the light bulb makes the dog produce saliva, and it doesn't. It doesn't get learned. It seems that the already learned combination of the bell blocks the learning of the light. And that challenges the idea that learning is just dependent on temporal contiguity. But we have some models, for example, the Rascorla-Wagner model, which I'll talk about in a minute, which offers an explanation for this. Okay, then another phenomenon is higher order conditioning, which is when a previously learned conditioned stimulus is used as an unconditioned stimulus to condition a new CS. So basically we have learned the bell association, and then we use this bell instead of the food to condition the light bulb. So now we turn on the light bulb and then we ring the bell. And since the bell has already been learned, it leads to the dog producing saliva, and then it learns to associate the neutral stimulus, the bell, with producing saliva as well. And those are a bit difficult to learn and practice, and usually also require the first order association to be shown in intermediate trials. So to keep showing the bell with the food in between, so the association between bell and food keeps active. And just another example for conditioned reinforcement is money, for example. So we work for money because of its worth that we derive from having it. Having a note of paper is in itself not really worth anything, but there's this higher order conditioning that we can derive worth from having this money. Okay, now let's get to the Rascorla-Wagner model. It's an influential theory in animal learning because it can account for effects like blocking without more elaborate cognitive theories. And the idea is that an animal only learns when an event violates its expectations. So in the case of blocking, the occurrence of the unconditioned stimulus, so the food, is already predicted almost perfectly by the bell. So we already know the bell means the food is going to appear soon. If we add now a light bulb, it doesn't help us predict the food any better. We already predict the food almost perfectly, and there's no extra surprise just because we have this light bulb added to it. So that would be the explanation of the Rascorla-Wagner model for blocking. And
Viviane, what do you mean by blocking?
So it's basically this idea here that when we have already learned the association of bell to food, and now additionally we present an extra neutral stimulus to also predict the food, this association doesn't get learned because we already have the bell-food association. So we show now bell and the light bulb together, and then we give the food. And if we test now the light bulb, it didn't get associated with the food because we already have the bell association. If we would just train the light bulb without learning the bell before, it would work. It would learn the light bulb predicts the food.
Okay, thank you.
Sure. Are there any other questions? Okay, feel free to interrupt me. So yeah, thanks for the question. Okay, so the model is a model on trial level, so it doesn't look at changes within the trial. So it doesn't look at what is the timing between the stimulus onsets, what is the time that is between different trials. It just looks on the trial level, and a trial is defined as the presence or absence of all stimuli. So it's defined as a feature vector x of s, and basically x is a vector, and the ith element of this feature vector. So S is kind of the trial type. The eth element is 1 if conditioned stimulus I is present. So in our example, we could have X be have two elements, one for the bell and one for the light bulbs, and it's either on or off depending on whether the bell and the light bulb is present. In the trial. Okay. And the idea now is to adjust an associative strength vector W for each component of the conditioned stimulus, which then expresses how strongly or reliably that component is predictive of the unconditioned stimulus. So we associate with this vector X, we associate a weight vector W, which tells us how predictive the presence of the bell or the presence of the light bulb is of the appearance of the food. So yeah, let me give you some formulas for this. So first of all, if we have multiple conditioned stimuli present, so if here both of these would be 1, then we use the aggregate associative strength. And the aggregate associative strength for trial type S is defined like this. So we write it kind of like the approximate value function here from the lesson yesterday. So the value of trial type S given our associative strength vector is the transpose of our weight vector multiplied with our feature vector of state S. So we basically just multiply the weight vector with the feature vector, and this gives us how much prediction we have, or how much evidence do we have for the unconditioned stimulus to appear. And the learning then happens by updating this associative strength vector W. So to the old weights, we add, we have again a step size parameter alpha, and then we add to this the TD error, or the prediction error, which I'll write down in a moment, multiplied with the feature vector of the current trial. So that means that only the associative weights of the elements of this vector here that were actually present in the trial are being updated. So if the light bulb was not present, for example, then this associative vector won't get updated in this trial. Okay, and what is this prediction error? It's kind of like the TD error from yesterday. It is, so we write an R here, but it now doesn't need to be a reward necessarily. It just expresses the prediction target, so the presence or the magnitude of the unconditioned stimulus. So in our case, this would be whether the food is present or not. So 1 if the food is there, 0 if there's no food being presented. Okay, minus this prediction that we made based on the stimuli that were present and our associative strength vector at time t, and here at time t plus 1, so the next one. Oh, sorry, I wrote this. Oh, no, sorry, that was actually right. Time t. Okay, so just the difference here between the target of the prediction, so the food, and the magnitude of the prediction that we made with this value estimate here. And yeah, Paria?
I'm so sorry. I think I missed what was the alpha?
Yeah, alpha is the step size.
Thanks.
So basically it tells us how much do we want to update our weights after each trial. So how much do we want to learn from this trial?
I see. Thank you. Thank you so much.
Sure. And so basically we update the associative strength vector with every trial and learn through this. And essentially this is kind of like least mean square error correction learning rule. So we try to make the prediction error as close to 0 as possible, which is similar to curve fitting or regression, just that we work with Booleans here in our feature representation and not with continuous numbers. Does that make sense so far? Okay. All right, so this model can account for things like blocking, for example, but there's an extension to it, which is the TD model, which generalizes this Rascorla-Wagner model by adding a time component. So now we can model in real time, and we can account for event timings within a trial and also between trials, which can be very useful to model, for example, classical conditioning experiments where we want to represent the trace interval or the interstimulus interval because they can have an effect on learning. And it is a theoretical model that we can use to try and explain or predict results from classical conditioning experiments. And the relationship here can go both ways. So on the one hand, the findings from behavioral experiments were used to inspire the TD model, But then again, the TD model was also used to make new predictions and inspired new experiments in behavioral psychology based on the predictions you can make with this model. Okay, so higher order conditioning is naturally accounted for in this model. It's not included in the Rascorla-Wagner model, but in the TD model it is accounted for due to bootstrapping. So because we update estimates based on other estimates, we can propagate the value estimate earlier to earlier states, which is basically what we need for higher order conditioning. And I'll talk about this more in a bit. And yeah, the state representations can basically, they can include external stimuli like the bell or the light bulb, but they can also include history-dependent patterns of internal neuronal activations in the brain. Since we have a model now, we can also use it to look at the effect of, for example, discounting or eligibility traces, and make predictions on results from conditioning experiments. Okay. So again, we have the aggregate associative strength vector, similar to the Rascorla-Wagner model, but the updates to these weights are different now. So now we update them like this. So again, we have a step size, alpha, and we again multiply this with our TD error, which I'll write down in a moment. It looks a bit different now. And this then gets additionally multiplied with an eligibility trace, Z. That is like the trace I talked about yesterday from TD lambda, but I'll also write down the definition down here in a moment. Okay, so the prediction error is again like in the Rascorla-Wagner model. We'll put it like this, and you can still see it. So we again take the prediction target, RT plus 1. Oh, sorry, I think here it was actually just the current reward. Okay, so next reward plus the discounted value estimate of the next state under the current associative strength vector minus the current value estimate. So this is like in TD learning now, only that yeah, the R now stands for the prediction target. So for example, presence of food, and it doesn't necessarily need to be a reward. Okay, and the eligibility trace changes dependent on the features that are present in each time step of the trial and decays over time. Okay, so basically an update to the eligibility trace is made by multiplying our discount factor gamma with our trace decay parameter lambda, multiplying those two with the eligibility trace, and then adding all the features that were present in this trial. So the trace is incremented whenever a feature is present in the trial, and then this incremented trace decays exponentially over time, similar to TD lambda from yesterday. So basically it's the same as TD lambda with a linear function approximation, except that the reward here doesn't need to be a reward necessarily, but it's the prediction target. Okay, and is this clear so far? Are there any questions? Okay, so now we can use this model to make some predictions on experiments or to try and explain experimental findings. First of all, we need to define how we want to represent stimuli. And there are 3 common ways to do this. The presence representation is the simplest way to represent stimuli, where you just have one element in the feature vector, which is on if it's there and off if it's not there. Then we have the complete serial compound, which is the most often used representation when modeling dopamine-producing neurons. And this is like, it has multiple elements in the stimulus representation, so we can account for the timing of the stimulus, and we can associate a different strength to, for example, the stimulus onset or later points in time of the stimulus. And then we have the microstimuli representation, which is similar to the complete serial compound, just that it smoothes this out a bit over time, and it is the most biologically plausible representation. Okay, and even with the simple presence representation, the time difference model produces all the basic properties of classical conditioning. So what are those properties? So the unconditioned stimulus must occur after the onset of the neutral stimulus. It doesn't help if we give the food and then a bit later we ring the bell. That doesn't associate the bell with the food, because the bell doesn't have any predictive value for the food anymore. So we need a positive interstimulus interval. Then after conditioning, the conditioned response begins before the appearance of the unconditioned stimulus. So the conditioned response anticipates the unconditioned stimulus. So the dog starts to produce saliva a bit before the food is actually presented. Or, for example, if we condition, I don't know, a rabbit to close its eyes because we puff some air into its face. I don't know why, who comes up with this. So you puff some air into the face after a signal, and the rabbit learns to close its eyes shortly before it anticipates the air puff, and doesn't have the eyes closed the entire time since the indicating stimulus. Okay, and then another property of classical conditioning is that the strength of the conditioning depends on the interstimulus interval. So first of all, it must be positive, like we already said, and the conditioning gets weaker with longer interstimulus intervals. So if we ring the bell and then half an hour later we give the food, this leads to a weaker association than if we ring the bell and then a few seconds later we present the food. Does that make sense so far? Okay. So now let's get to some simulations and experiments. So we have, in experiments, we find an effect called serial compound conditioning. So when the trace interval between a conditioned stimulus and unconditioned stimulus is filled with a second conditioned stimulus, the conditioning of the first CS is facilitated. So what does this mean? So we can always think of this unconditioned stimulus as the food now, in an example. And then let's say CSA and CSB are a bell and a light. So the point that serial compound conditioning makes is, if we have a light, then we have a break, and then we give the food. This association between light and food is learned better if in between we have another stimulus. So we have a light, then it turns off again, then we have a bell, stops, and then we have the food. And this is found in experiments. And if we now use the TD model to run a simulation here, we can see the same results. So if CSB is present, the association here, the associative strength between CSA and the unconditioned stimulus gets stronger than if CSB is not present. Okay, so there the TD model matches the experimental findings. Then we have something called the primacy effect, which says when there are two overlapping CS with CSA starting earlier than CSB, the presence of CSA reduces the conditioning of CSB. So again, think of this as the light, the bell, and the food. And it says if the light is on and it stays on until the food, and then shortly before the food comes, we also ring a bell, then the conditioning of the bell to the food is not so strong if the light is also there already before the bell rings. Because if we think again, back to the idea, if the bell is already earlier there, it is already enough to predict the food, and the additional bell doesn't give us a lot more extra information for the prediction of the food, because we already have the light there. And we find this in experiments, and we find it also in the simulation. So the associative strength here between the bell, for example, and the food is stronger when the light, which would start here before, is not there than if it is there. Okay, and then another effect, blocking, that we already talked about a bit earlier. We already said that the Rascorla-Wagner model accounts for it because there's no prediction error anymore that would lead to any learning. And the TD model accounts for it for the same reason. It's also similar to the Rascorla-Wagner model, an error correction learning rule. So it learns from the prediction error. And additionally, the TD model also makes an extra prediction, which is cool because this prediction was actually made before an experiment was conducted, and the prediction from the TD model was actually used to design this experiment and tested, and then the experiment confirmed the results from the TD model. So the TD model predicts that blocking is reversed if the onset of the blocked stimulus is moved earlier in time, such that it starts before the blocking stimulus. So what does it mean? Again, think of this as the light, the bell, and the food. If we already have conditioned the bell and the food, so they're already fully conditioned, or the association is already learned, which means the associative strength between the food and the bell is already high. And then we add a light, which starts before the bell. Then this light is actually not blocked and is actually conditioned because it allows an earlier prediction of the food. And we can see now that the associative strength between here, the bell, and the food actually goes down if we have an earlier predictor of the food, so the light here. Okay. And lastly, let's talk about higher order conditioning again. So using an already conditioned stimulus as an unconditioned stimulus to condition a new neutral stimulus. The TD model can account for this with bootstrapping. And the idea is, okay, we have here again the bell, which is already conditioned. So we already learned that the bell produces salivation, and then we add the light, and we don't present the food anymore, so there's no unconditioned stimulus presented here. And we just use this bell as the unconditioned stimulus to condition this light bulb. And here are the model results. So the associative strength of the bell starts out high because we have already learned it, and then it decreases because bell and food are not presented together anymore. So this is also called extinction trials. So since bell and food are not presented together anymore, the bell doesn't have that predictive value anymore, and it loses the associative strength. In the beginning it has it though, so in the beginning it can be used to increase the associative strength of the new neutral stimulus, so the light bulb, and then this decreases again because the associative strength of the bell decreases. And that's also why it helps to insert first order trials. So it helps to have trials in between where the bell appears together with the food to keep this this association here strong and not have it decay so fast. So we can keep learning from it and use it as a secondary reinforcement. Okay, and then we can also look at the timing of the conditioned response. So in animals, usually the magnitude or probability of the conditioned response increases as the expected time of the unconditioned stimulus decreases. So the salivation is the strongest right before the food is presented, or the rabbit blinks most likely shortly before the air puff comes. And in simulation, we can now see that this actually depends a bit on which kind of stimulus representation we use. So if we use the complete serial compound representation, we can see this effect pretty nicely. In the presence representation, there's only one associative strength that we can learn for each stimulus, so we can't model many features of the timing. So it's just, we can't model this feature. And in the macrostimulus, we can see that it approximates the CSC representation after about 200 trials. And this shows the importance of which representation we actually use. So small details in the model, like the representation or the discount factor or the eligibility trace decay factor, can have an impact on what results we actually obtain. Okay, so overall, especially when we assume a more complex stimulus representation, the TD model can help account for many subtle phenomena of classical conditioning with a pretty simple mechanism. And but the TD model can't account for all properties of classical conditioning and needs to be extended to incorporate some effects by, for example, adding some model-based elements to it or mechanisms to adaptively alter some of its parameters. And also Bayesian models are a really interesting alternative to TD models to model those kind of behaviors. Okay, so this will be the part on classical conditioning. Are there any questions to this?
Yeah, I have one rather general question. And
Yeah.
that is, yesterday I have not completely understood the aspect of bootstrapping in, for example, the TD models. So what is exactly meant with bootstrapping in that case?
Okay, so that basically means that we update estimates based on other estimates. So same as in dynamic programming. So in dynamic programming, we solve the value updates recursively. So we look recursively at the different action possibilities from each state, and then from the next states, all the action possibilities, and do this update value estimates based on others. And the same is here in TD. We use here this next value estimate in order to update the current value estimate by updating these weights. So we use estimates to update other estimates.
Okay, yeah, that was helpful. Thanks.
Sure. All right, so instrumental or operant conditioning goes back to Thorndike's law of effect, and Skinner termed it operant conditioning. And basically the idea is that learning depends on the consequences of behavior. So in classical conditioning, the unconditioned stimulus or the food is delivered independent of the behavior. And in instrumental conditioning now, the delivery of the reward depends on the behavior. And one example is this puzzle box that I have this really old picture from here. So you put a cat into the puzzle box with some food standing outside of the box, and the cat has to perform a sequence of 3 actions to open the box. So for example, it has to push down a platform, pull on a string, and push a bar up or down. And then the box opens. And in the beginning, the cat acts random, just trying anything to escape the box. And then on successive trials, it gets faster and faster at opening the box, because it can update its policy based on what actions led to a good outcome. And the most simple version of this is the Skinner box, which is basically just a box with a lever inside. And if you press the lever, a reward is released, usually a drop of juice or something like that. Yeah. And reinforcement learning and instrumental conditioning have two features in common. They are selectional and associative. Selectional means alternatives are tried out and selected based on their consequences. And associative means selected behavior is associated with certain states to form the agent's policy. So just to compare to some other learning mechanisms, so evolution, for example, is selective. So it tries out alternatives and select them based on their consequences, but evolution is not associative. So it doesn't select behavior, it doesn't associate the behavior with certain states to form a policy. And for example, supervised learning is associative, but it is not selectional. So it needs a teacher to make the selection for it. And we have the effect of shaping. So that's a little bit similar to what Leon talked about yesterday with curriculum learning, but now in animals. So to train an animal, it can be easier to train them by first reinforcing approximations of the desired behavior. And this can lead to faster learning, especially if the desired behavior doesn't come out naturally. So for example, with the simple Skinner box, where the mouse needs to press a lever, you can first reward it if it goes close to the lever, then you can reward it when it touches the lever with any part of the body, then when it presses down the lever. And so it can learn it faster, especially if it just doesn't naturally happen that it actually presses down the lever with its paw. And this can also be useful in reinforcement learning, especially on difficult tasks, to gradually increase the difficulty and first reward just approximations of the desired behavior. Okay, and then we also have the factor of motivation. So for example, in this box here above, the cat had some food standing outside, which motivated it to want to escape. And in reinforcement learning agents, sometimes there are internal motivation states used. So yeah, you can imagine a hungry rat runs faster than one that just ate. But most of the reinforcement learning agents nowadays just use motivation expressed as trying to maximize cumulative reward. So it's always the same kind of motivation they have. And it doesn't depend on if they just ate or not. Okay, then we also have something called delayed reinforcement. So in biology, learning is also possible when there is a significant time interval between the conditioned stimulus offset and the unconditioned stimulus onset. So you can also learn without having an immediate reward after the behavior, but you can have like a pretty large interval actually between the desired behavior and the reward for it and still learn it. And to solve this in reinforcement learning, or to explain it in general, we need to solve the credit assignment problem proposed by Minsky, which is how to distribute credit for success between many decisions that have been involved in producing it. And this is one of the big problems in reinforcement learning in general that we try to solve. And in reinforcement learning, we address this problem by using eligibility traces. So keeping in mind kind of a short-term memory of what we did recently, and with TD methods to learn the value function, so to propagate the value over the states close to the rewarding state, so that the states surrounding the rewarding states also have a higher value estimate, which provides almost immediate evaluation of actions and immediate prediction targets. And there are corresponding mechanisms proposed in animal learning as well. So we have, in animals, we observe trace conditioning, which basically means that the trace interval is a big interval, and still with this delayed reinforcement, the animals can still learn. And it is assumed for this to happen that this is only possible if the conditioned stimulus leaves a trace in the nervous system that persists until the unconditioned stimulus onset. And this kind of trace is proposed in different ways, to be realized in different ways. So for example, there are Hull traces proposed in 1932 already, which propose that animals' actions leave internal stimuli whose traces decay exponentially over time. So this is very similar to the eligibility traces that we used in TD lambda. So we have a trace that goes up when we see a stimulus, and that keeps kind of in mind that we saw this recently, and it decays over time and then disappears again. And then we also have the Klopf traces proposed in 1972 by Klopf. And they are kind of eligibility traces that are temporally extended traces of the past activity at synapses. And they are a bit more complex than the Hull traces. And I'll talk about them more in the next section on reinforcement learning in neuroscience, because they're kind of on a synaptic level. Here, then we also have cognitive maps, and they can kind of be compared with model-based reinforcement learning algorithms, where they have some elements in common with them. And basically, we can observe latent learning, which means, for example, we put a rat into a maze without any rewards, and the rat just explores in this maze without having any rewards for anything it does. And then after exploration, food is introduced into the maze, and the rat solves the maze faster than without exploration, which means that something has been learned during the no reward period. So the rat must have learned something, even though there were no rewards presented to it during the exploration period. And Tolman, 1948, put out the theory that the animals can learn a map without rewards, which can then later be used for goal-directed behavior. And the idea of how they do it is that they learn stimulus-stimulus associations during this exploration. So there's this expectancy theory, which says that if we have these stimulus-stimulus associations, then the occurrence of a specific stimulus generates an expectation about the next stimulus. And that can then be used for goal-directed behavior. And those stimulus-stimulus associations can be learned supervised without any reward signals by just using the first stimulus as the input and the next one as the prediction target. So we don't need any supervision or reward signals for this. Okay, and then lastly, we also have the study of, in general, habitual versus goal-directed behavior, and those two can kind of be compared to model-free and model-based reinforcement learning. So model-free RL being kind of like habitual behavior, and model-based RL kind of like goal-directed behavior. And habitual behavior is faster and more efficient, but with goal-directed behavior, we can adapt faster to environment changes, because we have a model of the environment, and if the goal changes or the certain aspects of the environment, we can replan using our model. And both can be used in one animal at the same time, and goal-directed behavior can also turn into habitual behavior if it is repeated often enough. Okay, and there are many other intersections of reinforcement learning in psychology, for example, decision-making or ecological and evolutionary aspects, and very interesting, of course, also multi-agent reinforcement learning and communication. But I don't have time to talk about all of these now, but I hope you saw that there are some really interesting intersections and overlaps, and both fields kind of influence and inspired each other at different points in time. And yeah, this would be the first section. And now we can talk about some questions and then make a short break before the second part about neuroscience.